Hi, welcome to another video on enzyme kinetics. In the last video I showed you how you could use Python to fit enzyme kinetic data to a Michaelis-Menten equation, and I've got the script here that we wrote. Let me run it and you'll see what it does. So in this figure here on the right you'll see a graph. The blue points are the experimental data. The error bars are the uncertainty in those experimental data points, and the orange curve is the fitted Michaelis-Menten curve. Now, the experimental data is fake experimental data. It's generated by taking a perfect Michaelis-Menten curve and then adding noise to it. And so the perfect curve has a Vmax of 20 and a Km of 15, and then we generated noise by drawing numbers from a normal distribution with a mean of 0 and a standard deviation of ST, and then we added that to the Michaelis-Menten data, and that gave us the quote experimental data. Okay, and I can run this again and it'll generate new experimental data and I'll get a slightly different result. With that experimental data, then I ran it through the curve fitter, and then results were plotted and printed out. So here we see the orange curve with the blue lines representing the experimental data, and then below it are the values for the fitted values. So in this case, actually, the Km is actually quite bad. It's 11.66, but it should be 15. The Vmax is much better at 20.01, which should be 20. This is often the case, in fact, that there are certain situations where the Vmax can be wildly out, but the Km is often the most difficult one to get right, and you can see that here where the Vmax is pretty good but the Km is pretty bad. And these things down here, these are the confidence limits, or the standard deviations, I should say, of the Vmax and Km, and they represent how the noise in the experimental data propagated into the Vmax and Km fitted values. So if I run this again, I'll get I'll get another set of values. This time the Km is much better. Okay, so what I want to do now is to show you what happens if we compare the Lineweaver-Burk plot to nonlinear fitting. So I've got this other script here. I'm not going to write this out because it's a bit long, and I'll just go through how it works. So at the beginning, it's similar to the last script. I got an actual enzyme with a Km of 15 and a Vmax of 20. I define the Michaelis-Menten function, and then there's a difference here. Then I have this big loop, and this loop iterates for 8,000 times. And what it's doing is it's generating, each time it runs through the loop, it generates a new set of experimental data and then does a fit. And each time it does a fit, it collects the resulting Vmax and the Km. Can I do this 8,000 times? So we just have a quick look at this. I've got some empty arrays here, and this is what I'm going to use to record the fitted Vmax and Kms. And then here I'm creating the experimental data, the fake experimental data, drawing random numbers from a normal distribution and adding those to the actual perfect Michaelis-Menten curve. So I get some noise in the data. I then do the fit. I then save the fitted parameters to this list, two lists, VMNF and KMNF. So I'll have 8,000 estimates for the Vmax and 8,000 estimates for the Km. I do exactly the same thing now, but using a Lineweaver-Burk plot. This time I have to plot 1 over the reaction velocity versus 1 over the substrate concentration versus 1 over the reaction velocity, and I need to use linear regression to then find the best fitted line through those points. I'm using sklearn package as a source of my linear regression algorithm, and that's quite a convenient one to use. So down here we invoke the linear regression module and then we do the fit. And I supply it with xt and yt, which is 1 over s and 1 over v. I also have to compute these errors. I'm not going to explain how this was done, but the errors have to be slightly modified because the y-axis is transformed by a reciprocal, and so the errors have to be similarly transformed. But anyway, once I do the fit, I can get access to the intercept and the slope. Okay, and of course the Vmax is just the reciprocal of the intercept, and the Km is actually the slope divided by the intercept. And at the same time, I'll save these estimated Vmaxes and Kms to two other lists, VMLW and KMLW. So just to repeat, I do this 8,000 times. I end up with 8,000 estimates for the Km and Vmax using both nonlinear curve fitting and doing the Lineweaver-Burk plot. So once we're out of the loop, we can then start analyzing the data. These two routines are just little helper routines to help me print out nice looking numbers, and also it helps me compute the percentile. Okay, so actually let me run this. So this section here is for plotting. So I'm just going to comment this out. Comment that out, and I'm just going to run it, right, to see what happens. Okay, it takes a while because it's got to compute 8,000 estimates. Okay, here we go. So it's outputted two sections, one for the nonlinear curve fitting, one for the linear regression. What it's gone and done is it's taken, so if you look over here at the script, excuse me, it's taken all the Vmax values and computed the mean for the nonlinear fitting, taken all the Kms that were estimated from the nonlinear curve fitting, computes those means. It does the same thing for the Lineweaver-Burk plot, where it takes the mean of the Vmax and the mean of the Kms, and this is what I'm picking up on the right hand side here. So it estimates that the mean Vmax from 8,000 attempts of nonlinear fitting is 20.034, and then likewise for the Km. I do the same for the linear regression, as I said, and these are the numbers for the linear regression or the Lineweaver-Burk plot. And you'll notice they're slightly worse than the nonlinear curve fitting estimates. Not much worse, but slightly worse. Now, what's more interesting are these 95% ranges. So the way I computed those was I computed two percentiles at 2.5% and 97.5%. So the data between these percentiles represents 95% of all the data, and there's sort of confidence limits on our data that we generated. And this will give me the ranges then, a lower range and an upper range. So you can see that the Vmax for the nonlinear curve fitting ranges between 18.556 to 21.618. You notice that the Km range is much wider, and this is actually often the case. For linear regression, though, you notice that the ranges have widened out, and quite a bit in the case of the Km. So this is one of the downsides of using the Lineweaver-Burk plot, and that is your uncertainty in the Vmax and Km will be larger than you'd get with a nonlinear curve fitting. All right, and this is one reason why people don't recommend you use Lineweaver-Burk plots to estimate Kms and Vmaxes. They're good for, the Lineweaver-Burk plot is good at getting a visual impression of what's going on, but for actual estimates of the for the Vmax and Km, it's not recommended. So now let's carry on. I can look at these numbers in another way. I can actually plot various things out. So let me uncomment this code. Let me run it first to show you what it gives me. So here should come any minute now. Here we go. So there's two banks of plots. The first is a 2x2 and the second is a 1x2. The 2x2 is basically plotting the distribution of all the Kms and Vmaxes that were estimated during the 8,000 iterations. So the top two are the Vmax and the Km for the nonlinear fitting, and the bottom two is the Vmax and the Km for the Lineweaver-Burk plot. And the thing to notice is, because look at the Vmaxes first. So the Vmaxes are pretty smack on 20. So 20 is the ground truth for the Vmax, and these distributions are pretty much sitting on 20. But you'll notice that the distribution for the Vmax when using the Lineweaver-Burk estimation is wider. If we look at the KMs, we see a similar thing. They should rest themselves roughly above 15, which they seem to be doing. But you'll notice that the distribution for the KM that came from the Lineweaver-Burke plot is much wider, and there's actually a upper long tail. And this is one reason why, for example, the estimates here are slightly worse than the estimates from the nonlinear fitting, but it also explains why the percentiles are much wider for the Lineweaver-Burke, simply because the distribution is much wider. So that's one way to look at the data. Now the other way to look at the data is to ask ourselves, okay, given an estimated Km and Vmax with a given level of uncertainty, how does that result in computing the reaction velocity, and how uncertain then is our reaction velocity that we compute? So this is what these orange curves are showing. So this is a plot for the reaction velocity on the y-axis and the substrate concentrations on the x-axis. So this is just a hyperbola. The left-hand one is for the nonlinear fitting, and the right-hand one is for the Lineweaver-Burke fitting. The black line is the mean of the reaction velocities from those 8,000 estimates for the KMs and Vmaxes. And you can probably see that the Lineweaver-Burke mean is slightly lower than the mean for the nonlinear fitting. But what's most noticeable are these orange bands. So the orange bands represent 95% percentiles on either side of the mean, and you see that the percentiles are quite narrow on the nonlinear fitting, but are much wider on the Lineweaver-Burke fitting plot. And this again reflects the fact that when we looked at these ranges are wider than the nonlinear fitting ranges. And so we're seeing that here. And so this is the other issue with the Lineweaver-Burke plot. Well, we've got two issues here. One is that the mean reaction velocity is slightly below what we should get, and the confidence in the reaction velocities are much wider if you use estimates from the Lineweaver-Burke plot compared to the nonlinear fitting. It might be of interest to show you how I did these plots. These histograms here were pretty straightforward to use. I created a subplot, 2x2 subplot, and then in each subplot, which was indexed by these two variables here, so 0, 0 represents the top left-hand corner, 1, 1 represents the bottom right-hand corner, and for each one I drew a histogram using the 8,000 estimates for either the Vmax or the Km. The 60 is the number of bins that we use, and the range is the range on the x-axis from 0 to 50. I wanted to make sure that every x-axis had the same range, so it was easy to compare the histograms. So that's all it takes to plot these distributions. It's quite straightforward. It's more tricky to do these, what I call these error envelopes. So it requires some effort. So the first thing I had to do again was compute the histogram data. So this time I wasn't going to plot the histogram data, I just wanted to collect the numbers. And just to show you what that looks like, if I print out the Vmax histogram data, you'll see it's basically a frequency of values. So the lower range, there aren't many values in the low end, there aren't many values in the high end. Most of the Vmaxes are clustered in the middle. Okay, so that's just plotting, that's just computing the histogram data. And I do that 4 times for each of the 4 parameters. So effectively I've just generated this data, but I've stored it in a variable. So what I do now is there's a very clever routine in the SciPy stats package called RV histogram. What it does is to take a discrete distribution like this and turn it into a continuous probability distribution. Now that's handy because once I have one of those, I can draw random numbers from the distribution. So what I do here, then I generate the histogram data, then I use this RV histogram to generate the actual distributions. So what I'll do is I'll draw random Vmax and Kms from these distributions and use them to compute a reaction velocity. I'll do this many times across different substrate concentrations, and I get these plots. Now, how did I do these plots? Well, once I have the probability distributions, I first create the subplot, a 1/2 subplot. I then draw samples from the Vmax distribution and the Km distribution, say in this case for the nonlinear fitted estimates, and draw samples is one of these routines up here I wrote. So there's two routines up here. So this is draw samples. All this does is it draws 200 Vmaxes and Kms and then returns them as a row in a growing list. So if and those estimates are returned as a p-list. If I show you what p-list looks like, you might explain it a bit better. So draw samples, right? This one here returns a p-list. A p-list is a list of rows, basically. And the first column represents the Vmax I sampled, and the second column represents the Kms I sampled. So this, for example, is a single pair, as a pair of a Vmax and a Km that I drew from this distribution here. I drew the Vmax from this distribution, and I drew the Km from this distribution. And I do this 200 times, so I end up with 200 samples of Vmaxes and Kms. Okay. Once I've got that, I need now to propagate these sampled Kms and Vmaxes into the Michaelis-Menten equation to get a reaction velocity. And this is what this function propagate errors does. So it takes the p-list, this thing here, and it'll return an array containing the substrate concentrations, xt, the mean at each of those, the mean reaction velocity at each of those substrate concentrations, and the upper and lower percentiles at those substrate concentrations. Okay, and it does this by, this is the routine here, propagate errors. It sets up some arrays, empty arrays, and it works its way through different substrate concentrations from 0 to 1 in steps of 1. Then at each substrate concentration, it takes in this case I'm only doing 100, but it takes 100 of these parameter estimates and computes the reaction velocity and stores them in an array called xt. Once it's done that, then it computes the mean then from that array of xt's and computes the percentiles from that yd array. Okay, it goes through that for all substrates and packages them all up and returns them. And the last thing it does is it takes all that data, plots the mean, which is the black line. Here's the black line. And then to plot the band, there's a function called fill between, which will take the upper and lower limits of the band. I set a color to orange, and it'll then draw the band for me. It's a very useful function for doing that. And so I end up with these two bands. Okay. So one thing I should mention is another thing about the Lineweaver-Burk is it can be unstable sometimes. And by that I mean it just gets the parameter estimates horribly wrong. This is an example I've got here. So this is the same program we had before, except, yeah, the same program as I had before. I've raised the standard deviation a little bit to 1.7, so that's the error in the data. So this data has a bit more error in it than the previous one. And I'm only going to run 800 because I'll show you what happens. So the band on the Lineweaver-Burk plot has gone a bit crazy. These are more spiky because I'm only doing 800 iterations. But what's happened is a couple of the fits have gone really badly wrong. One of them is this one here. So, and I think this is at, yes, it's the 654th run in the iteration. It produced this data. So this is the Lineweaver-Burk plot. This is 1 over V versus 1 over S. These points are not too bad, but then this one is looking a bit crazy. And in fact, it's biasing the entire linear regression. The linear regression should be fairly shallow, right? But because of this this point here, it's actually much steeper than it should be. In fact, it's so steep, it runs very close, the intercept runs very close to 0. In fact, the intercept is this number here, which is 0.00069. And of course, the reciprocal of that, which is the Vmax, is huge. So in fact, this is the reciprocal. This is the Vmax, 5,331, which is a bit crazy. So you can get problems like this, and the reason why this is happening is because at the upper end of this axis, the 1 over s, the velocity becomes quite sensitive to slight errors in the substrate concentration. And so the errors sort of get magnified, and they end up with things like this. And so you have to be careful when you're using the Lineweaver-Burk plot. You should inspect the raw data to see if you're seeing anything strange like this. I mean, you'll see more scatter as you go from left to right, but sometimes you'll see these aberrant points that just don't look right. So you have to be careful with a Lineweaver-Burk plot, and actually, ultimately, I don't recommend you use it at all. It's good for visual inspection, but it's not good for estimating Vmax and Kms because of these issues. Now, when it was first devised, it was at a time when there weren't any computers, and doing straight line fits could be done manually, so it was a useful operation to use. But now that we have, computers everywhere, there's no real excuse for using a Lineweaver-Burk plot to estimate the Vmax and the Km. Instead, I always recommend doing non-linear curve fitting, and as we saw in the previous video, it's not difficult to do anymore. It's pretty straightforward now. Okay, so I think that's it for now. I hope that was clear enough. Let me know if it wasn't. Okay, thanks very much.